So, what is a set exactly? Well, I try to give my students everyday concrete examples. So, the easiest way to think about a set are, things in everyday life. So, think of a set of golf clubs. So, a full set of golf clubs has a driver club in it, it has a 7-iron in it, it has a putter in it, usually. So, a set of golf clubs is a bunch of different other clubs, which we would call elements, and we'll talk about that in a minute. So a set of golf clubs, or a set of dining dishes. So here we have 3 plates and a cup, and they come in a set from the store. Or a set of wizards. I put that in there for fun, but it can be true too, a set of wizards. So think of things which are grouped together based on some criteria that makes them similar. So if we go buy a set of golf clubs at the sporting goods store, we're not going to open up the box and find a bag of dog food. Likewise, if we go to the store and we buy a set of dishes in the box and we open up the box, we're not going to find a pair of bedroom slippers, because that obviously does not go with the set, most likely. And of course, in a Harry Potter movie where we have a set of wizards, we don't expect to see a set of Ewoks from Star Wars walk through the movie. So a set is just a group of similar things based on some criteria, and that's the easiest way to think about it. Now, of course, in mathematics classes, we have more formal definitions, okay? So let's go ahead and look at these graphically and in terms of how we notate them. So we're going to have a set here, which we're going to call set N. And inside this set, it's kind of like a fence around these numbers. And inside this set N, we have the numbers 1 through 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, the individual things inside the set are called elements. So 1 is an element of set N, 6 is an element of set N, 4 is an element, etc. So the individual things inside the set are called elements. Now we write that in this manner. So set N equals, and then in braces, we list the elements. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now this symbol is one that throws students for a loop because, unfortunately, sets and counting and set notation is often skipped in many high schools. So my students are always like, I've seen integral calculus, but I've never seen this symbol. Well, the good thing is this symbol is very simple. All it means is an element of. So for example, 4 is an element of set N, because there it is, right there in the middle of our set. Now there's sort of an opposite symbol that looks like this, and it means not an element of. So for example, the number 12 is not an element of set N. So basically these symbols just tell us whether or not individual elements are members of a set or not. Now let's talk about equivalent sets. So we have our same set N over here on the left. And now we're going to have a new set M over there on the right. So in set N, we have the same 9, or the same numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9. Over here on set M, we have the same thing, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are equal to each other. They are equivalent. So M equals N and N equals M, because M and N have the exact same elements. So if we list the elements in set N, 1, 2, 3, 4, 5, 6, 7, 8, 9. If we list the elements in M, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. They are equivalent sets. Now it's important to note here that the order in which we list the elements does not matter. So I could list N as it is, but I could list M as 987654321. It doesn't matter. The order does not matter in terms of how you list the elements. Now let's talk about subsets. Now, I just want to point out here, there is sort of this confusing part of subsets that I'll have to explain in a later slide. So just hang with me for subsets. We'll talk about proper subsets and empty sets in the next couple of slides, and then in sort of a summary slide, it will all sort of come together. So if it seems confusing now, just hang with me. So we have our subset, or set, I'm sorry, over here in, set in. Our same numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now over here we have set E, which is 2, 4, 6, and 8. Now notice that everything that is in E is also in N. So 2 is in both of them, 4 is in both of them, 6 is in both of them, and 8 is in both of them. Now when we go ahead and learn how to draw Venn diagrams, there is a graphical way of representing this. However, since we're just learning about sets in general, we'll skip over that for now. But E is a subset of N because everything in E is also in N. Now the symbol we use for a subset is sort of this C shape with a line underneath it. Now what we're saying here is that E can be any subset of N, including the equivalent set. And this is where it gets kind of weird. Now obviously set N and set E are not equivalent, but set E is a subset of set N. But also, if you remember in the previous slide, we had set N and set M, and they were equivalent. And in terms of subsets, they are subsets of each other. So you can think of it as a twin. So here are our sets here, and an equivalent set is a subset of its twin. And again, this is where it can get kind of confusing, but hang with me. There's a slide at the end that kind of summarizes all this in an easy-to-use table. So E can be any subset of N, including its twin. Now, it's also including its empty set, but we haven't talked about empty sets yet, but we will here in a second. Now let's talk about proper subsets. So we have our set N over here, the same thing we've been doing, and we have set E over here on the right. It's the same two sets we had in the previous slide. Remember we said that E is a subset of N, which is true. Now E is also a proper subset of N. So we have subset and proper subset. Well, what's the difference? Well, in terms of our nomenclature and our symbols, we use this symbol. So it's kind of the C shape, but there's no line under it, and there's an important reason why that is. Now, E can be any subset of N, including the empty set. So E would qualify here, but E cannot be equivalent to N. And that's the primary difference between subsets and proper subsets. For all practical purposes, sets and subsets are the same thing, except when it comes to proper subsets, the equivalent sets don't count. So equivalent subsets are not proper subsets. So again, we'll look at that in the table here in a second, and it should make a bit more sense than me trying to say set, 1,000 times. Now, empty sets. So here we have our set N again, and our numbers in there. And over on the side, we have another set, Z, but it is empty. There's nothing in it. So we call that an empty set. So it's often written with this symbol down here below. Now that's not 0. Okay, that's sort of the null. That symbol sort of means null. It means empty. So it's kind of a 0 shape with a line through it. Sometimes it's just two braces with nothing in there. It's sometimes written like that. But that's an empty set. So Z, remember this symbol, Z is a subset of N. So the empty set is a subset of N. It's also a proper subset of N. Because remember, they're not equivalent, so the proper thing doesn't get in the way. So the empty set is both a proper and a basic subset of any set. Now every set does have an empty set as a subset. So whatever set we have, over here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Of course, an empty set is a subset of n. Over there we could have, all the oceans on the world. But we could still have an empty set that is none. That is none of them. So Z is a subset of any set. And actually of every set. Okay, so here is going to be a table that will hopefully bring all this together in a nice, easy to read format. So let's say we have a set J, and it contains the numbers 0, 1, and 2. Now we can make many subsets out of those numbers. So we'll call that subset set K. So set K could be empty. Set K could just have the 0. Set K could have just the number 1. Set K could have just the number 2. Set K could be the numbers 0 and 1. Set K could be 0 and 2. Set K could be 1 and 2. And set K could be the equivalent, which is 0, 1, and 2. So those are all the possible subsets we could make from set J. Now if you notice, everything is both a subset and a proper subset until we get down to the equivalent set, or the evil twin. So the equivalent set 0, 1, and 2 is a subset of J, but it's not a proper subset of J. Because if it's equivalent, it's not a proper subset. So the easiest way to think about subsets versus proper subsets is this table. The only real issue comes into play when the sets are equivalent. If they are equivalent, then it's a subset, but not a proper subset. Okay, just briefly talk about infinite subsets. Now, some sets have an infinite number of elements, and it'll be written like this. So this would be set I. It could be 1, 2, 3, and then it goes on, theoretically, into infinity. So an infinite set does not have a finite number of elements. It keeps going on to infinity. Let's talk about set notation for certain outcomes. We often use set notation to represent a list of outcomes for, say, an experiment. So let's say we flip a single coin. Well, our set of outcomes would look like this. It could be heads or tails. Or a single die roll. Our set of outcomes could be 1, 2, 3, 4, 5, or 6 for each side of the die. If we're looking at a stock's movement from day to day, or even hour to hour, or minute to minute if you're a day trader, the set of outcomes could be the stock goes up, the stock remains even, or the stock goes down. Now look at this one. If we flip two indistinguishable coins, okay, so we don't pay attention to the year on them or something like that, we just treat them as if we can't tell them apart. So what are our set of outcomes here? Well, we could have heads, 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 tails, or tails, tails. Now, why did I highlight the middle one in red? Well, if we're using coins that are indistinguishable, heads, tails, or whatever, there's only one outcome for that. So, since we can't tell the coins apart, it's just heads, tails. But what if we flip two coins we can tell apart? Well, it would look like this. We could have heads, heads. Now remember, the order doesn't matter, so that's one outcome, heads, heads. Or we could have tails, tails. Same thing there. But look in the middle. We could have heads on coin 1, tails on coin 2, or heads on coin 2 and tails on coin 1. Because those are two different coins. So we would have this extra outcome. So we often use set notation to represent a list of outcomes for an experiment. Now, set builder notation is sort of a way of writing out what we want in our set. So, for example, we have a set C, and what we're saying is that it's full of elements, and these elements are odd integers less than 10. So n is an odd integer less than 10. So knowing this description, we can come up with the set C that is 1, 3, 5, 7, and 9. And that's called set builder notation. We don't use it a whole lot, but you do see it sometimes in your work where it comes up when you least expect it. So this one could be a set P, and N is one of the 8 planets. So set P would be Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Of course, Neptune is my favorite planet, so there it is. So you can see that set builder notation is sometimes an easier way to represent sets in sort of plain English. So I'll talk about intersections. That's where these problems become interesting, and this is probably how your problems are set up in your class. So here we have N, and here we have E. So set N and set E. Now, if you notice, they overlap here in the middle. But the thing is that neither set is totally inside or nested inside the area of another. So there is no subset here. There will be some elements of N that will be outside of E. So if you look at the diagram here, everything that is in the pure orange color is only in N. Now there will be things that are in E but outside of N. So the part of the diagram that's just blue, those things are just in E. But what about the middle part, sort of the purple where the colors come together? Well, that is our intersection. And anything in that area belongs to both. It belongs to both sets. So let's take a look at that further. So let's say we have a set A, and it's the numbers 1 through 9. Then we have the set B, which are the numbers 6 through 14. So 1 through 9, and then 6 through 14. So the question is, what elements do these sets have in common? What elements do they share? Where do these two sets overlap? Well, if we look, they have 6, 7, 8, and 9 in common. Those are the elements they share. Now, if I write these sets so they actually overlap, so I line up the 6s, I line up the 7, line up the 8, line up the 9, what I can do is actually show where they overlap, where they have in common. So I can put a little graph there. So 6, 7, 8, and 9 are where they have their elements in common, where they overlap exactly. So 6, 7, 8, and 9 belong to both sets. The numbers 1, 2, 3, 4, and 5 only belong to A. So only in A. And the numbers 10, 11, 12, 13, 14 are only in B. So we have sort of 3 regions here. In the middle, we have the intersection. We have the overlap, the things in common, which are 6, 7, 8, and 9. Then we have numbers that are only in A, 1, 2, 3, 4, 5, and numbers that are only in B, 10, 11, 12, 13, and 14. Now, if we actually put this in a Venn diagram, it looks like this. So as you can see in the middle, we have 6, 7, 8, and 9. The area that's only A, sort of the very dark orange part, we have 1, 2, 3, 4, and 5, just like our graph above it. And then over on the right, we have the numbers 10, 11, 12, 13, and 14 just in the pure blue over there on the right. Now, we do have to make sure that our original sets are intact. So let's make sure we look at set A. So do we have the numbers 1 through 9? Well, we have 1, 2, 3, 4, 5 in the just A part, and then we have 6, 7, 8, and 9 in the overlap part. So if we kind of put our hand over the just blue part where B is, we can see that A does indeed have the numbers 1 through 9. Now check B. Does it have the numbers 6 through 14? Well, it has the numbers 10, 11, 12, 13, 14 in the just B part in the blue, and it has 6, 7, 8, 9 in the intersection. So if we put our hand over the orange part and we just look at the intersection and the pure B part, we have the numbers 6, 7, 8, 9, 10, 11, 12, 13, 14. So again, we can look at it a couple different ways to show how this intersection is represented in just a general sort of graph up there in the upper right, or in the actual Venn diagram in the lower right. So a little bit more about intersections. What we say is these are the elements these two sets have in common. Now another way we can say it is that these elements must be in A and in B. In A and in B. So A is 1, 2, 3, 4, 5, 6, 7, 8, 9. B is 6, 7, 8, 9, 10, 11, 12, 13, 14. So what elements are in both? What do they have in common? So we say A intersect B, and remember that's the intersect symbol down there, so an upside down U. A intersect B equals the set 6, 7, 8, 9, or that intersection. And that's how we write that. So this is how we do very simple intersection using two sets that overlap and have elements in common. Now what about unions? So intersection is what they have in common. Union is a little bit different. Now the way we put this is that the elements in just A, they're in the orange, just B, they're in the pure blue, or both, and that's the intersection in the middle. So anything that's in just A, just B, or both. So we can also say the elements must be in A or B. Now in mathematics, we use the or as inclusive. So we really are saying they have to be in A or in B or both. So A is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is this region right here, the A circle outlined in the green. B is this area. Now notice that down in the B set down there, I crossed out the 6, 7, 8, and 9. Well, why did I do that? Because when we're doing a union, we're interested in sort of what's in the whole thing. But we can't count those numbers twice. We're only going to count them once. So when we say, what is A union B, it's all the numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So all those numbers appear either in just A, just B, or both, or the elements are in A or B or both. And we don't double count the intersection where they overlap. Now in the next video, we're going to talk about cardinality. And that's where this comes into play when we can figure out what parts of our diagram we are missing. So just keep in mind that the union is basically anything that appears in that region once. And then we just count that up, and that is our A union B. So if we really kind of take everything out, the numbers and the colors and everything like that, the union is basically this shape here. So depending on where you are in the world, you may or may not have what are called peanuts, but we have those here in the US. And this is kind of a peanut shape, or some people will call it like a bean shape. So we have what's in A, what's in B, or what's in both. If we kind of, again, erase all the lines, this is the sort of overall area we're interested in. Now disjoint sets, there is no subset. Okay, there's no intersection. They're completely separate. So in this case, set N, intersect E, okay, is null. It's empty. So there is no intersection between N and E. And of course there's no subset because they don't overlap in any way. So these two sets have no elements in common, because they do not overlap. And there are no subsets or anything because one is not inside the other. But remember, an empty set is a valid set. It's actually a very important set in many instances. But an empty set is a valid set. So you might get a question that says, what, and here's the diagram, and they go, well, what is N intersect E? And the answer isn't 0. The answer is not, does not exist. The answer is not whatever. The answer is empty. N intersect E is empty. It's an empty set. Now let's talk about the universal set. So basically, the universal set contains all the elements we're interested in. And it really just depends on the problem. So you might have a problem that's about all the clothes in a store, or all the students in an academic program, or all the restaurants or other businesses in a certain region in the U.S. So the universal set kind of puts a boundary around all the things that will be under discussion or that we are interested in. And again, it really just depends on the problem. Now, inside that universal set, we can have all kinds of subsets and intersections and unions and all kinds of stuff. So think about this. Everything that is in S, some of them are also in A here. So all of A is inside our universal set. There'll probably be some things in A and some things outside of A. So if an element is in S, but it is not in A, so it's sort of in the orange floating around outside there, then we call that the complement of A, which we denote with A prime. And we'll put numbers in here in a second. So everything in S can either be in A or not in A. Now there will be nothing outside of the universal set. So everything in the universal set has to be in either A or not in A. So let's look at this. Now look at our universal set. Look at all the numbers in that rectangle, including what's in A, because of course A is in S, so we have to count it. So that's the numbers 1, 2, 3, 4, 5, 6, 7, and 8. Now what is in A? Well, A alone are the numbers 2, 4, 6, and 8. And of course, those also belong to S because it is inside S. Now the question is, what is A complement? What is in the universal set S but not in A? So A prime. Well, those are the numbers 1, 3, 5, and 7. So that's just, again, that's just the idea of the complement of a set. So whatever is in A is in there, of course, but there are still things outside of it in the universal set, so they are not in A. Now, of course, you'll have problems, and we'll do them in future videos, that involve the intersection of 3 sets. So this is a very common graphic you're going to be looking at doing all these Venn diagram problems. Now, I just kind of started to give you a hint of some of the things you're going to be finding. So if you look in the middle here, we have set A, B, and C. And right in the middle is where they all 3 overlap. So A intersect B intersect C. Now here are a couple bonus questions. What regions are A intersect B? So you have to be just careful. You have to develop a vision for doing this. So A intersect B. Let's look at A, the circle for A. Then we look at the circle for B. Now what region, in what regions do they intersect? Well, one region they intersect is what we have labeled, A intersect B intersect C. But there's also one more region where they intersect. You see it? Okay, that is the region to the upper left of A union B union C. So it's kind of a darker green color in the upper left. That's also part of A intersect B. So basically, what this becomes is like a puzzle you have to solve. Venn diagrams where we have missing values and we're given certain values, we have to use set relations and set operations to sort of figure out the missing pieces of a puzzle. And I've always wondered why puzzle books don't have Venn diagrams in them, because that's exactly what they are. It's all about finding the missing pieces so all the parts add up to what we know they should be, what we have in the problem, etc. But we'll do these in future videos.
In this clip, we're going to look at some special notation used in Venn diagrams. The first bit of notation looks like this. When you see this symbol here, which looks a little bit like a lowercase n, it means the intersection of A and B. So on the Venn diagram, I would shade in this section here if I was asked to shade the part that represented this. The next special piece of notation is this, and it looks a little bit like a lowercase u. This means the union of A and B. So that's everything in A and everything in B as well. So I need to shade in everything in A and B. The final bit of notation is this. Now this means the complement of A, but you might like to think of it as meaning not A. So shading this on the diagram would look like this. You'll see that I've shaded everything that's outside of the A circle. So to summarise, this means the intersection, that's this part. This means the union, that's everything in A and B. And this means the complement of A, or not A, so that's everything outside of A. Here are some for you to try now. You'll need to copy the Venn diagram 3 times and then shade the appropriate parts. Press pause and have a go. When you're ready, press play. So for A, we want the complement of A, that's everything that's not in A, united with everything that is in B. So everything that's not in A is this, and I need to include everything that's in B as well. So we also need to shade in this part, and this is the finished answer. For part B, we want the complement of A union B. So this is everything that's outside of A and B. So that's this. For C, we want the complement of A intersect B. So that's everything that's outside the intersection of A and B. So this is the answer for that one.
So here is our first problem. Now let's take a look at the anatomy of the Venn diagram so we completely understand how it's laid out and what's going on. So the first thing we notice is that we have a universal set. That's everything within the square shape. So everything we're going to consider is inside that square shape. Now inside there we have 3 sets. We have set A, then we have set B on the lower right, and then we have set C in the lower left. And it appears they all intersect at various points. So we have the 10, the 2, and the 4. So we are given some basic information to work with. Now, of course, our job is going to be to fill in the missing regions. So you can see we have several missing regions. The majority of A is missing. The majority of B and C are missing. And then we have part of an intersection between B and C missing. And of course, we have everything outside of A, B, and C also missing. So there's quite a bit of information we got to fill in. Now, of course, in addition to what we're given in the regions, we are also given some more information. Now, the first thing we're told is that the number of elements in the entire universal set must add up to 50. So everything within that square must add up to 50. Now, we're also told that the number of elements in A must add up to 20. Now, we're given part of A, because the 10, 2, and the 4 are part of A. They're part of other things too, but they're definitely part of A. So we can use that information to fill out our missing part. We're told the number of elements in B is 20. So if we look at the B set down there on the lower right, we have part of it. We're given the 2 and the 4. Those are part of B. The number of elements in C equals 28. So if we look at set C down there in the lower left, we have part of that. We're told that the 10 and 2 are part of C, but again, there are 2 regions missing there. Now we were also told that the number of elements in B intersect C equals 8. So the sort of the American football shape, kind of the oblong oval shape down there between B and C, that must add up to 8. So we can use the information we're given, both in the diagram and in the list over here, to find out the missing piece. Now, there are also some things we can figure out from the diagram that isn't given to us in the list over there on the right, but based on the diagram, we can come up with some more knowns. For example, we know that the number of elements in the triple intersection, or the intersection of A intersect B intersect C, there in the middle, we know that is 2. Now that was not given to us in the list over on the right, but based on the diagram, we can put that as a known. We also know that A intersect C is 12. So if we look at set A and set C, their intersection is accounted for with the 10 and the 2. So we know that A intersect C is 12. On the other side, we know that A intersect B is 6. So if we look at the A set and the B set, their intersection is accounted for with the 2 and the 4 over there on the right-hand side. So we have 4 unknown regions we have to find. Actually, 5, I'm sorry. We have T, which is up here in the A. We have U over down in the C set. We have V, which is in the intersection of B and C. And we have W, which is down here on the lower right. Now, in addition to this, and this is my fault, we also have one more. You know where that's at? Well, it's on the outside. So anything outside of A, B, or C is going to be in the region between the A, B, and C sets and the universal set, sort of on the outside. So that's my fault for not putting that in there. I do apologize. Okay, so let's talk about how to find this first missing piece. So we're going to try to find the part of A that is unknown. Now we know that the number of elements in A has to add up to 20. So we can find that missing region using subtraction. So if the entire part of A has to add up to 20, we can subtract the 10 that's accounted for here in the left. We can subtract the 2 that's in the triple intersection there in the middle. And we can subtract the 4 that is common to A and B. But of course, it's still in A. So 20 minus 10 minus 2 minus 4 equals 4. So the number of elements in that missing region, that part of A that we didn't know, is 4. And that should sort of make sense if we add up everything we have. 10 plus 2 plus 4 plus 4 equals 20. So that's the first piece we found. Now let's try to find this missing part of the intersection between B and C. Well, we're given in the problem that the number of elements in B intersect C equals 8. Therefore, the missing region there in the blue has to be 8 minus 2, which gives us 6. So that missing piece is 6. So in our given, B intersect C is 8, so 2 and 6 is 8. Now let's find the missing part of B. Well, we know that B has to equal 20. Therefore, the missing region has to be the entire part of 20 that we're given, minus the 6, the 2, and the 4 that we already know. So 20 minus 6 minus 4 minus 2 equals 8. So the missing part of B is 8. Now we're going to find the missing part of C. So we know that C has to equal 28. Therefore, that missing region is 28 minus the 10 we know, minus the 2 we know, and minus the 6 we know. So 28 minus 10 minus 2 minus 6 equals 10. So So we can put that there. So we're almost done. Now the next piece we have to find is outside, if there's any. So how do we do this? Well, we know if we add up everything that we have there inside A, B, and C, that is A union B union C. And if we add up everything in there, it comes out to 44. So if everything in the universal set is 50, and everything inside A, B, or C equals 44, then outside of that must be 6. 50 minus 44 equals 6. And that goes there. And guess what? That is the end of this problem. So before we do the second one, just some general things in mind. The easiest thing to do is just to make a list. Okay, and in the next video, I'm going to talk about that extensively. Make a list of everything you are given, and then make a list of everything you can find out from the diagram on your own. And then from there, it's just basically solving a puzzle. Okay, so you find the easy things that you can look at and say, hey, you know, I have everything in A but this one piece. And I know what A has to be, so I can find that one piece. And then you sort of go from there. So you find the easiest things first, and then go from there. Okay, so this is going to be a practice problem too, and this one's a bit more difficult because some of the things we have to find, we don't have a lot of information off, right off the bat. Let's go ahead and take a look at this one. Okay, so the same basic setup. So we have a universal set, which comprises everything of interest. We have 3 sets in the middle, A, B, and C, same thing as the last one. But then we have different pieces of information. So we have, outside of A, B, and C, we have 100. So outside of the union of A, B, and C, the elements are 100. But then we have bits and pieces of other parts of the Venn diagram. We have 2 parts of A. We have a 3 and 4 there. We have 2 parts of B, a 10 and a 4. Then we have 2 parts of C, a 15 and a 10. So you look at this and you're thinking, well, how I have 2 missing pieces for everything. How can I find that? So this is how we're going to do it. So here are some givens. The number of elements in the entire universal set is 140. Now, what we can discern from that, and it's actually given to us here, is that everything outside of the union of all 3 A, B, and C equals 100. And that's down here in the lower right. But that tells us something else, which we'll talk about here in a second. Now we're given that the number of elements in A equals 10. The number of elements in B equals 19. So again, if we look at A, we have 2 elements, or 2 regions out of 4. So we got to figure out what's going to add up to 10 there. With B, we know it has to add up to 19, but we only have the 10 and the 4 to work with. So, what can we find out just from what we have, which is not much, to tell you the truth. There's not much to go on at the start. Now, if the entire universal set is 140, and then the complement of the intersection of A, B, and the union of A, B, and C is 100. That's the 100 outside there. What does the union of A, B, and C have to be? Well, it has to be 40. So everything outside of that union of A, B, and C is 100. So everything inside has to be 40 to make up our entire universal set of 140. So it's the first piece of information that you can sort of discern from the diagram itself. So we'll go ahead and put that in our list of givens or knowns over here. So we have our universal set 140. We have the complement of the union of all 3 sets equals 100 down there at the lower right. That means we know that A union B union C has to add up to 40. The number of elements in A is 10. The number of elements in B is 19. So what can we do with this? Well, there are 3 regions we do not know. We don't know T here in the middle. We don't know U, which is over there in the intersection of A and C. And we don't know V, which is part of B. So those are the things we're going to have to try and find. Now the first thing we're going to do is we need to figure out a way to find, part of a missing piece. And one of the things that makes this Venn diagram challenging is that all of our sets A, B, and C have two unknowns in them. So we kind of have to work with what we have. Now, if you see what I've done here, what we know is that the number of elements in A has to add up to 10. So for that to be true, we know that the number of elements in this intersection here, which again, that is comprised of two unknowns, which I'll talk about in a second. But this little shape here in the green, well, that has to have 3 elements in it. So we can kind of put a 3 there temporarily. Now, we know that this region where the 3 is made up of 2 unknowns. But for now, that's not really important. This is just a temporary step, because when we fill in that 3 there, what does it allow us to find? Well, that allows us to find the value for V there in the lower right. So just this very simple acknowledgement that because A has to add up to 10, this little slice here on the left-hand side has to be 3. That would make A add up to 10. That frees us up to find V, which if you look at this Venn diagram now, that's the only unknown. That's the only unknown. So how do we find that? And I've gone ahead and colored it in blue here. What we know is that since A union B union C equals 40, we can use subtraction to find that bottom unknown. Should be bottom right, not bottom left. So 40, which is the union of A, B, and C, minus the 15 we have there, minus the 10, minus the 3, minus the other 3, minus the 4, leaves us with 5. So we know this region has to be 5. Now we could not have done that without this little trick of the part of A that is 3. That was the importance of that intermediate step. So the 5 there is what we found. Now we can move on to the next part. Now, since we know that B has to add up to 19, we can now find the unknown T there in the middle. Because since we found the 5 in B, now we can find the other unknown in B, which is T there in the middle. So use subtraction. So 19, which is the totality of B, minus the 10, minus the 5, minus the 4, leaves us with, believe it or not, 0. So the value of T, the value of the triple intersection there in the middle, is 0. Great, now we only have one more thing to find, and that is the part of the intersection between A and C there in the blue. And we can do this using A. Since we know that A has to equal 10, we can just subtract to find that last unknown. So 10, which is the entirety of A, we're given, minus the 3, minus the 4, minus the 0, leaves us with 3. So the unknown there in the blue section is 3.